positive 3y. In the other equation, we had a negative 3y. When we added the two equations, the positive 3y and the negative 3y canceled out, and we wound up with one equation with one letter. When we have that, that's okay. The problem is we don't always get equations that have nice situations like a positive 3y and a negative 3y. So in this lesson, we're going to look at a method that works anytime. And the reason I showed you the other three methods in the previous lesson was because there are some teachers who say, I want you to be able to do the various methods. And on a test, for example, they might say, solve this by graphing or solve this by substitution. I personally prefer to have my students solve it any way they can because the key is the solution. But just in case you have a teacher who wants to be sure that you know more than one way to solve it, we included those three methods in the last lesson. But this method always works. So let's take a look at an example of what we mean by elimination. And let's take a look at the first visual. We have two equations. 5x plus 2y equals 17. That should be in blue on your screen. And 3x minus 4y equals 5 is the equation in red. Now you'll notice that it might be very difficult to graph these two equations because they both would involve fractions once we got it in y equals mx plus b form. Also, it would be impossible, I think, to use substitution. Again, we'd involve fractions. I shouldn't say impossible. Some people love fractions. I am not amongst that crowd. We couldn't just simply add the two equations because the 5x plus the 3x would give us 8x, and the 2y and the minus 4y would give us negative 2y. We'd still wind up with an equation with two variables. Now the question is, how do we eliminate one of those letters? That's the way it's called solving through elimination. Well, I think you can see that it probably is easiest to eliminate the y. Why do I say easiest? Because you'll notice two things about the y coefficients. One, they're opposite signs. So if they were both the same number with opposite signs, we could add them and they would cancel each other out. But they're opposite signs, but they're not the same number. One is a 2 and the other is a 4. But immediately we recognize, hey, if we multiply 2 by 2, we get 4. So we can multiply that 2y by 2 and get 4y and add the two equations. We eliminate the y's. We have an equation with one letter, x, and we solve for x. The problem is, remember, we can't simply multiply one term in an equation. We must multiply the entire equation. So the third line in that visual, we see that we've multiplied the top equation, 5x plus 2y equals 17, by 2. We have 10x plus 4y equals 34. We now have two equations that can be added, and when we add them, they will eliminate one of the letters. So let's go to the next visual, which shows us doing exactly that. We've added 10x plus 4y equals 34, and 3x minus 4y equals 5. We can do that. Remember, when you add two equations, you're adding equals and you get an equation. In this case, the equation is 13x equals 39. Now, 13x equals 39, we can solve. Again, the goal of this method is to eliminate one of the two variables, leaving us with an equation with one variable which we can solve. There is no equation of this type that we cannot solve. So, in fact, we get x equals 3. Of course, we're not done. Why are we not done? Because a solution to a system of equations means you get both x and y. So we need to solve for y. And how are we going to do that? Well, the next visual shows us that. Indeed, we have x equals 3. We have the original equation, 5x plus 2y equals 17. Notice I've gone back to the original equation, and we plug in x equals 3. 5 times 3 is 15, plus 2y equals 17, 2y equals 2, y equals 1. Once again, we're solving an equation with one letter in it. We can do that. And thus, finally, our answer, 3, 1, the ordered pair. You can look at this as a point on the graph. Had we graphed these two equations carefully, the intersection would have been at x equals 3, y equals 1. And x equals 3, y equals 1 is the only values of x and y that will work in both equations, which should remind us that the last thing we need to do is to check. And we check by replacing the x and y with the values that we've solved for. We could do it in both equations, but since we've used the first equation to solve for y, it isn't totally necessary. If you'd like to do it, that's fine. But the next visual shows us that indeed we've only checked in the second equation. And we replace the x with 3 and the y with 1, and 3 times 3 minus 4 times 1, 9 minus 4 is 5. So it does check. So again, that was the simplest example of elimination. I guess the only simpler example would be what we did in the previous lesson, where we just had to add the two equations. Here we only had to multiply one equation, so that we then had two equations. When we added them, we eliminated or canceled out one of the variables. The next situation we're going to run into is where it takes a multiplication of both equations. But we're still not reaching the ultimate kind of problem, because in the next problem, although we have to multiply both equations, we will have one of the letters that has opposite signs. And we'll see that the most difficult, and it really isn't that difficult, type of elimination process is when you have two equations and you have to multiply both equations, and both equations have the same signs in front of the letters. So let's take a look at the next visual, the next problem to be solved. And we have two equations, 5x plus 4y equals 12, which is in blue, and 3x minus 5y equals 22, which is in red. Notice that the x's have the same signs, but the y's have opposite signs. In the top equation, the y is positive. In the bottom equation, the y is negative. So at least we don't have to worry about changing signs. But we cannot simply multiply one equation. In other words, we can't multiply 4 by something and get 5. Well, actually we could, but it would be a fraction. And again, I don't like fractions. The reason I don't like fractions is all my years of teaching, most of my students really don't like fractions. So we try to avoid working with them. So what we need to do here is actually multiply the top equation by one number, and then multiply the bottom equation, the second equation, by another number, so that the two y terms have the exact same coefficient but opposite signs. That is, we need to multiply 4 by something and multiply 5 by something else and get the same number. This may have you recall back when you were learning fractions in elementary school. We talked about the common denominator. And in fact, that's the same thing. We're looking for a common multiple of 5 and 4. And certainly the easiest common multiple of 5 and 4 is 5 times 4, which is 20. So what we really want to do here is be able to get the two y's, so one is positive 20 and the other is negative 20. And in order to do that, we need to multiply the top equation by 5. That will give us 20y. And we need to multiply the bottom equation by 4. That will give us negative 20y. And in the next visual, we see this. We've multiplied the top equation by 5, the bottom equation by 4, and below that, we actually have the multiplication. We have 25x plus 20y equals 60. Now you'll notice we're beginning to work with some pretty big numbers, but it's for a good purpose, because ultimately we will get an equation that we can solve. And the second equation multiplied by 4 is 12x minus 20y equals 88. We add the two equations up, the plus 20y and the negative 20y cancel out. And we're left with 37x equals 148, and we divide both sides by 37. At this point in time, you're saying, gee whiz, those are pretty big numbers. Well, if you have access to a calculator, fine, but if you don't, you recognize that the answer works out pretty nicely. X equals 4. So we've eliminated the y's, we've solved a simple equation in one variable for x, and now it's time to get y. And at this point in time, let's go ahead and do this at the board, because sometimes it's nice to see it worked out directly. So we have our two equations. We have 5x plus 4y equals 12. Again, these are the original equations. And we have our second equation, 3x minus 5y equals 22, because we always go back to the original equations. We've solved for x. X was 4. We want to solve for y. Now, I ask you, which of these two equations do you think I will choose to solve for y? It really doesn't make a difference which one you choose. But if you've followed along with me, I don't like to work with fractions if I can avoid it, and I don't like to work with negatives if I can avoid it. Notice there's no negative here. There is one here. So I will use the first equation to solve for y. And again, I can solve for y when I get an equation with only y in it and numbers, so I can solve an equation with one variable. Let's see. Well, if x is 4, 5 times 4 is 20. And let's see, 20 plus 4y equals 12. Now we have an equation, one letter, easy to solve. Subtract the 20. 12 minus 20 is negative 8. Divide both sides by 4. And we get y equals negative 2. Okay. So now we have our solution. X equals 4. Y equals negative 2. I'm going to erase this because we have one last thing to do in the solution of this system of two equations. And of course that is to check. Okay? We could check here, but I'm not going to. And the reason is we just use this equation to solve for y. Notice, had we not used one of the two original equations to solve for y, but let's use one of the equations where we had multiplied by a number, then we'd have to check in both. But since I used this equation already to solve for y, I simply need to check in the second equation. 3 times x is 12. Negative 5 times negative 2 is plus 10. And indeed, 12 plus 10 is 22. Again, had we gone back to the method of graphing, had we graphed 5x plus 4y equals 12, and had